पब्लिक करने पे चल जाएगी।
OSIRIS-REx in NASA's repertoire. I like to call it the Daredevil spacecraft.
10 seconds. 9, 8, 7, 6, 5, 4, 3, 2, 1. And liftoff of OSIRIS-REx. Its 7-year mission to boldly go to the asteroid Bennu and back. Liftoff of OSIRIS-REx. Its 7-year mission to boldly go to the asteroid Bennu.
Good afternoon, everyone. Welcome to today's media briefing on the upcoming asteroid sample return of NASA's OSIRIS-REx mission. I'm Patrick Lynch with NASA's Office of Communications, and I'm joined today by mission representatives from NASA, the University of Arizona, and Lockheed Martin. We're broadcasting today from inside a hangar at the Army's Dugway Proving Ground in central Utah. And 24 days from now, in the high mountain desert of the Utah Test and Training Range, several miles behind us, the OSIRIS-REx mission will deliver to Earth America's first ever sample from an asteroid. The mission team earlier today completed a drop test with a replica sample return capsule. And today they will share details of that test in addition to details of the final preparations toward the sample return. The climax of a 7-year journey, from the 2016 launch at Kennedy Space Center to the sample collection at the asteroid Bennu in 2020 to the return to Earth here on September 24th. With us today we have leaders of the OSIRIS-REx mission. Melissa Morris, the program executive at NASA headquarters. Rich Burns, project manager based at NASA's Goddard Space Flight Center. Melissa Morris, Sandra Freund, Lockheed Martin's program manager for the mission. Kevin Ryder, the OSIRIS-REx deputy curation lead at NASA's Johnson Space Center. And finally, Dante Lauretta, the mission's principal investigator based at the University of Arizona. After remarks from our panelists, we'll open up to questions from the media in the room and on the phone line. For those on the phone, you can press star 1 to get in the queue and ask a question. For those in the room, you can raise your hand. We'll bring a microphone to you. And with that, I will turn it over to Melissa Morris.
Thank you, Patrick. I am so very excited to be here as we head into the final stretch of the delivery of these valuable and long-awaited samples back to Earth. As you may know, NASA's goal for science is to create a global community for exploration and discovery that fosters innovation and inspiration. And to that end, NASA invests in small body missions like OSIRIS-REx to investigate the rich population of asteroids in our solar system that can give us clues about how the solar system formed and evolved. It's our own origin story. And remember, the O in OSIRIS-REx is for origins. The planetary science mission fleet is huge, with nearly 40 missions. And 3 of those missions to small bodies are being showcased this fall in something we're calling Asteroid Autumn. In September, we have, of course, the delivery of those samples from Bennu by OSIRIS-REx. And in October, we have the launch of the Psyche mission to a never-before-seen metal-rich asteroid. And finally, in November, we have the Lucy flyby of an asteroid in the inner main belt, with providing a test of their innovative autonomous terminal tracking system. And so OSIRIS-REx, we're kicking off Asteroid Autumn. OSIRIS-REx is a part of the Planetary Science Division's New Frontiers program, which supports medium-sized missions that are competed and PI-led. OSIRIS-REx was a result of the New Frontiers 3 announcement of opportunity. It was selected in 2011. It launched in 2016 spectacularly, on time, and arrived at the asteroid Bennu in 2018 to begin an 18-month survey of the surface of the asteroid, in part to select a sample site for collection. And those samples were successfully collected in October 2020, and then OSIRIS-REx headed home with the sample in 2021. And guess what? We're just a few weeks away, get a little bit clumped, from the delivery of those samples to the Utah desert. And so OSIRIS-REx is a phenomenal mission. It has achieved so much already. It's the first U.S. mission to return samples from an asteroid. And that sample mass collected is the largest from beyond the orbit of the moon. And on a personal note, this mission is so important to me. It's directly applicable to my research into the formation of the solar system and early solar system materials, in particular components that can be found in meteorites that are thought to come from parent bodies that are very much like Bennu. So I am so excited to see what's in these samples. And I'll turn it over to Rich for a project overview.
Thanks, Melissa. I'm Project Manager Rich Burns. I'm at NASA Goddard Space Flight Center. I've been the project manager of OSIRIS-REx since launch. It's been an extraordinary journey of adventure and exploration. This mission is one pure exploration, meaning we didn't really know much about Bennu before we launched, so it surprised us in just about every dimension. Dante called it the Daredevil spacecraft. Well, all daredevils practice, and that's what I'm going to talk to you about a little bit today. At least all daredevils that live to tell the tale, right? And we are survived coming home. So we're very excited to be in the final phase of this long journey, 7 years, as you saw. The journey started even before that. Dante's been running this marathon for a very long time. So how do we prepare? The Roman philosopher Seneca said success is when preparation meets opportunity. We're very fortunate to be in the position to be privileged, really, to be a part of this mission of exploration. So we take very seriously our preparation. The preparation consists of both tests and rehearsals, maybe indistinguishable to a lot of people, but we call tests when we're practicing commanding with the spacecraft, but we use a simulator instead, much as a pilot would fly a flight simulator. Rehearsals, we put our team in the field, in the environment they're going to be in, using the communication tools and the equipment they're actually going to use on the day of recovery. And you're going to see some of that from us in the upcoming graphics. Today, as Patrick mentioned, we conducted a drop test from a helicopter. So we dropped a replica, as you see right here. This is the real replica that we dropped from the helicopter about 7,000 feet altitude. It deployed its main parachute. This represents the final phase of flight for OSIRIS-REx sample return capsule and the sample being delivered home under the main chute. The descent is quite gentle from this point forward. It comes screaming into the atmosphere, but this main chute slows it down significantly. This is our first opportunity to work with our colleagues at the Utah Test and Training Range to track the capsule as it descends under the main parachute using the sensors that are here at the range. That worked beautifully to locate the sample, the location of the landing, and then recover the capsule from there. Yesterday, we placed the capsule on the range and practiced our recovery techniques. And here you see we are recovering the capsule with 4 helicopters that deploy our recovery team. First, to ensure the area around the landing is safe and secure. And then the recovery team approaches the capsule to prepare it for transport back to a clean room, temporary clean room that we've assembled here at the range. This takes quite a bit of processing on the ground before the capsule is ready to be transported. Human safety, as you're going to hear from me in a bit, is our #1 priority. So we make sure that the capsule itself is ready for transport, prepare it, put it in a cargo net, and transport it back under a long line via helicopter to a building you saw this afternoon with a temporary clean room embedded in it. We land under that long line, and the capsule itself gets transported into the building and into the clean room itself for disassembly, and ultimately, as you'll hear, transport to our curation facility. We're very excited about this process, but let me tell you a little bit about what precedes the reentry. We have a major decision just 4 hours in advance of when the capsule enters the Earth's atmosphere. That's whether the spacecraft will release the capsule or not. That decision is based on 3 criteria. Human safety is our #1 priority, as I said. Capsule survivability. The environment, as you'll see, is very harsh during the atmospheric reentry. Capsule reenters at 12.3 kilometers per second and heats up very quickly. And then the third is landing accuracy. Can we land in the prescribed area that we know is going to be safe and free of people? So back in July, we started a sequence of maneuvers that are intended to target the Utah Test and Training Range. The first maneuver, conducted in July, targets a path, moves the path of the spacecraft to within 125 miles of the Earth. Then on September 10th, we'll target the Utah Test and Training Range, followed by a maneuver 1 week later to refine that targeting. And as you're going to see later, we have a very relatively small area to fit in, but we're highly confident we'll hit that. After we release the capsule, we make the decision at 2 a.m. in the morning, the day of release. We'll release the capsule at 4:42 Mountain Time, assuming we decide to release it. And then 20 minutes later, the spacecraft will make another maneuver to avoid Earth, and it will be on to its extended mission to a soon-to-be famous mission, or asteroid called Apophis. We're very excited about that extended mission. We're here to talk about the primary mission. Following all that, we will be targeting the Utah Test and Training Range. It's a beautiful place to land a sample capsule. Why? Because it's enormous. Its expanse is mind-boggling, really. Texas may not have much on Utah in terms of everything bigger. Utah is pretty darn big. So we will be targeting an area, an elliptical-shaped area, marked here as our expected landing area. We will have to be sure that the capsule will land in that area. We'll make that decision at 67,000 miles away from Earth. That capsule will be released at 67,000 miles away from the Earth. And we'll hit that landing area is about 250 square miles. It's the equivalent of throwing a dart across the length of a basketball court and hitting the bullseye. So with that said, I'm going to turn it over to my colleague, Sandra Freund from Lockheed Martin.
All right, thanks, Rich. So like everybody else on this panel, I'm really excited that we are less than a month away from returning these samples. So I'm going to take you back a little bit in time before we get on the ground. And just like the recovery team, our flight operations team is busy practicing and rehearsing everything that we need to do in order to ensure that the sample return capsule is released. So like Rich mentioned, we have that go, no-go decision point. We fully expect that decision to be a go at 2 o'clock in the morning local time on September 24th. So at that point, the mission operations team, which is located at Lockheed Martin in Littleton, Colorado, will be sending the commands to the spacecraft that will start the sequence to do all the events that are needed. So we have an animation here that shows actual release from the spacecraft. So we need to make sure that we configure everything, we're pointed correctly, and then we will let go of the sample return capsule. Shortly after that, as Rich mentioned, we will do a divert maneuver to make sure that the spacecraft bus does not follow the capsule in. We have a very long 4 hours from release until re-entry into the atmosphere. You can see there, we will re-enter at about 27,000 miles per hour over the Utah Test and Training Range. We'll deploy a drogue chute autonomously that will stabilize the capsule, followed by the main chute, and that's what we rehearsed today. That main chute gets us to a nice, gentle 11-mile-per-hour touchdown here in the desert. Our recovery teams will be standing by, waiting to get the all clear to go ahead and approach the capsule. So that series of events leading up to entry are shown in our next graphic. That breaks it down to what actually happens in the 13 minutes that it takes from when we enter the atmosphere until we make that gentle touchdown here in the desert. So our recovery team is made up of people from Lockheed Martin, NASA, curation, and folks from the Utah Test and Training Range. They're standing by. Once the capsule's on the ground, they will then approach it. Again, keeping in mind safety first for both people, followed by sample. We will take a look at the capsule, make sure it's safe to approach it. We'll approach it, do some initial checks out in the field, and then ready it for that long line flight that Rich discussed. Once we get it back into our clean room here at the Utah Test and Training Range, there'll be a little bit of disassembly that will take place. The primary goal to get the nitrogen purge onto our sample to keep it pristine. Then we will ready it for shipment. So it will be placed inside a specially designed shipping container where we will fly it the following day on a C-17 aircraft from here in Utah down to Johnson Space Center. So I'll turn it over to Kevin to talk more about the curation side of things.
All right, thanks, Sandy. So I'm Kevin Reiter. I'm the OSIRIS-REx Deputy Curation Lead from Johnson Space Center. And Johnson Space Center is the home of NASA's astromaterials. We have a lot of collections there. For example, the Apollo lunar samples, meteorites from Antarctica. We have comet samples brought back by the Stardust mission, and we have solar wind ions brought back by the Genesis mission as some examples. And we're very excited to have the opportunity here to add a new collection to our astromaterials collections, carbonaceous-rich asteroid material from Bennu. So the curation is all about keeping the sample safe and clean and uncontaminated. And our curation team has had two major activities related to the recovery. And I'd like to spend the next few minutes explaining those two and what our team has been accomplishing. So the first area is to aid in the recovery. And so some of the footage you see here is the rehearsing by the field recovery team, where we have curation scientists part of that team. They'll be collecting air, soil, and water samples around the SRC on return. And the reason we're doing that is to understand the nature of the landing site, and so that we can assess potential contamination later on. We want to have a really good understanding of where it landed and the composition of the material around the capsule. So in addition to the field activities, as Sandy alluded to, our team has established a clean room in a nearby building here, and the clean room will be where the capsule is brought in from the range. The clean room, we've been working on this for a couple of months. Activity started back in June, and we have now, as you can see, established a fully functional clean room ready to receive the sample. The purpose of the clean room is to allow our team to prepare the sample before it gets shipped off to Houston. And so we're really excited about that. So those are the recovery efforts. The other effort, major effort the curation team has been involved with, is establishing a new clean room in Houston. And you see some footage there from that clean room. The clean room was established as a dedicated clean room for this sample so that we do not cross-contaminate with other collections. So we will only have Bennu samples in this clean room. And you can see in the footage there are two main components to the within the clean room. There are two nitrogen glove boxes that the sample will be handled and processed in, and this is to protect the sample from contamination. Again, the goal is to be clean and uncontaminated. And so the first glove box you see there, the larger glove box, will be where the lid is removed from the sample canister. That will reveal the TAGSAM collector head that collected material directly from the surface of Bennu. Once that is revealed and removed, it'll be temporarily contained and transferred to a second glove box. In that second glove box, the TAGSAM will be disassembled, and that'll take some time, so it'll be a long several-week process to get in to reveal the bulk sample that lies within all of that hardware. So once that occurs, we will start to characterize the sample, understand better what we have, how much we have, how many different rock types and lithologies there might be within the sample. The characterization will be used to determine material that we allocate to international partners from JAXA and the Canadian Space Agency, as well as determining what material will be appropriate to allocate to the science team for their studies. And with that, I think I'll turn it over to Dante, who will tell you more about the science.
Thank you, Kevin. It's really amazing to be here today. I've imagined the series of events that we've been rehearsing for literally almost 2 decades. And I have the honor of sharing the stage with these amazing people, and they represent organizations that have brought hundreds of individuals to achieve this mission success. As you can see from the first graphic here, I've grown up on this program. I don't even recognize this kid from 2008 who was writing that New Frontiers proposal to convince the agency to let us lead this program to bring back these amazing samples from the dawn of our solar system. Launching in 2016 seemed like the highlight of my career at the moment, but it was really just the beginning of getting us to this incredible world, this small asteroid named Bennu that holds clues, we believe, to some of the deepest questions that we ask ourselves as humanity. Let's take a look at the asteroid. It's a stunning celestial object. To give you a sense of scale, it's about 500 meters or a little over 1,600 feet in size. That's about the size of the Empire State Building, or like a small mountain. I like to think of Bennu as a small mountain floating in outer space. And its shape is particularly intriguing. It literally is a droplet made out of rock, gravel, and boulders that are barely held together by their own microgravity. And it was amazing to have our spacecraft visiting this celestial neighbor for over 2 years with our prime focus of picking that key location on the asteroid surface where we sent the TAGSAM, the touch-and-go sample acquisition mechanism, which you can see here, the forearm of that device, make that brief contact with the asteroid surface. And it was a really dynamic event. Bennu, I call the trickster asteroid. It has challenged us every step of the way. We thought for sure we were going to touch down on a solid surface. This was an asteroid. It was a rock from outer space. But it actually responded more like a fluid, like if you dropped yourself into a ball pit at a children's playground. The good news was, because of that really soft surface, we collected an enormous amount of material. We promised the agency we would bring back 2 ounces, or about 60 grams of material. We believe, based on some very clever spacecraft engineering from our partners at Lockheed Martin, measuring the momentum change on the spacecraft as we articulated that robotic arm, that we have at least 4 times that material in that sample return capsule. So over 8 ounces, or about 250 grams of material. And boy, is the science team excited to get that. In addition to being the principal investigator, I'm also on the field recovery team. I wanted to personally be out there to greet these pieces of Bennu to our home planet, welcome them to the curation facility at Johnson Space Center, and get them ready for the adventure we're about to put them on. At the University of Arizona, we've been building world-class laboratory instrumentation. We have some state-of-the-art electron microscopes, ion microprobes, a whole suite of ancillary equipment. And one of the best parts about being at a university and being able to lead a program like this is that we're training the next generation, right? I've had over 200 students, undergraduates and graduates, working in science, engineering, analysis, chemistry, marketing, graphic arts, video production, business management, all of the skills that it takes to bring a mission like this to a close. And we have an army of graduate students that are waiting to get involved in the sample science program. It's really a great entry point for young people to get involved in science. They're super excited just to think that we've got these pieces of asteroids. And then I start to explain the story of what these samples are going to tell us. We're going back to the dawn of the solar system. We're looking for clues as to why Earth is a habitable world, this rare jewel in outer space that has oceans, it has a protective atmosphere. We think all of those materials were brought by these carbon-rich asteroids very early in our planetary system formation. And of course, the biggest question, the one that drives my scientific investigations, is the origin of life. What is life? How did it originate? And why was the Earth the place that it occurred? And because Bennu is so rich in carbonaceous compounds, we've seen these with remote sensing instruments that we used while we're at the asteroid, we believe that we're bringing back that kind of material. Literally maybe representatives of the seeds of life that these asteroids delivered at the beginning of our planet that led to this amazing biosphere, biological evolution, and to us being here today to look back on that amazing history, to think about where did we come from and where are we going? What does it mean to be alive, to be conscious in this amazing universe? Let's take a look at the last graphic. This is where we think it all began. We call this the protoplanetary disk. This is where stars are born. And when a star is collapsing, it spins out this disk of gas and dust, and that's where chemistry and physics start to work together to build initially dust grains, literally like snowflakes made out of rock and metal and sulfur and organic materials, ices that accrete together. They grow into asteroids and they grow into planets. So the asteroids that we have in our solar system today, they're left over from this earliest stage of solar system history. We're literally looking at geologic materials that formed before the Earth even existed, right? I call these like the grandfather rocks, the ones that really represent our origins and where we came from. And I know they've just been waiting for 4.5 billion years to get into that sample return capsule, get down to the Utah desert, safely get to the amazing facility that our colleagues at Johnson Space Center have put together. And Kevin talked about protecting, making sure they're pristine, but a big part of the job is also getting that material out to the scientific community. This is a gift to the world. We have laboratories on 4 continents, 16 time zones, hundreds of researchers, over 60 laboratories that have been getting ready to get this material, and we are ready to begin the final science campaign of the OSIRIS-REx Prime mission. So with that, I'll turn it back over to Patrick.
Excellent. Thank you for wrapping that up, Dante. Thank you to all the panelists. Let's get to some questions. Again, in the room, please raise your hand if you have a question. Sophia will get a microphone around to you. And if I don't see any off the... here we go, up here, Sophia. And for those on the phone, please press *1 to get in the queue. We will get to you shortly. Thanks.
Hi, I'm Yu Inoguchi for Kyoto News, Japanese news agency. My question is, you are going to exchange the samples with JAXA or Hayabusa 2 team. And what is, would you please explain a little bit about the importance of studying 2 similar but different asteroids rather than just one? And what you are looking forward to seeing through the international cooperation? Thank you.
I think I'll start. Maybe Melissa might want to say something as well. But I want to say we've had an amazing partnership with our Japanese colleagues and the Hayabusa 2 mission. We recognized early on that we were much stronger together and that the science return was going to be exponentially larger by having these 2 asteroids to compare and contrast with each other. So the Hayabusa 2 mission went to an asteroid named Ryugu. It actually looks a lot like Bennu. It's got that, what we call the spheroidal or spinning top shape, these fluids made out of rocks and gravel. And we exchanged lessons learned. We worked together defining our science programs. Rich and I and colleagues went out to visit JAXA to talk to them about how their sampling events went and take that information back to us. And already the Ryugu samples have provided amazing insights into the origin of the solar system. And I'll say, when I saw what Hayabusa 2 brought back, I was like, okay, that's really similar to the kind of material we have, but spectrally these asteroids look very different. So it actually made me think, well, what exactly are we bringing back? We might be bringing back something we haven't seen in our meteorite collections, and actually that's what I'm really getting excited about. Maybe, Melissa, you want to talk about the interagency cooperation?
Absolutely, and as I mentioned before, NASA really wants to be a part of a global partnership that does exactly what Dante says. We work with our partners. We're stronger together. We cannot do anything alone. I think we all know that. And to just play on that, two different asteroids that may photograph and look a little bit the same can be very, very different. And with my history with meteoritics, I think the thing that would make me the happiest is if we have something totally different. And you can have two meteorites that look identical and can be very, very different. And so it's so exciting to be working with both the Japanese and the Canadians, and we want to be stronger together to investigate these big problems and where we came from.
Okay, take our next question from the floor, right at the back. Oh, wherever you find him.
Hello, I'm Justin Davenport from NASA Spaceflight. We all know what happened to the Genesis sample return mission. Had issues getting back down. What have you learned since then that you've been able to apply to this mission?
I'll take that one. We have learned a lot from Genesis, right? Every success and every failure has lessons learned. We are very confident that we've taken the lessons learned forward from Genesis into OSIRIS-REx. We have done an extensive test program on our sample return capsule before we launched it, and continue to look very deep inside of the capsule to make sure we understand absolutely everything that's in there. Now, sample return missions are hard. There's a number of things that can go wrong. Our ground recovery team is ready for any scenario that is to happen. We fully expect that sample return capsule to land very gently on its main parachute, but they are prepared in the event that it is not.
Okay, let's take, go ahead and keep raising your hands. We'll move the mic around in the room. Next question we're going to take from the phone line. Marcia Dunn from the Associated Press, you are up. Go ahead.
Can you hear me there?
Yes, we're coming in now. Go ahead.
Oh, great. Yeah, thank you. Probably for Dante, I'm not sure. You mentioned 250 grams anticipated coming back. I keep reading about a cup of the material, debris, rubble, filling up. Would about 250 grams fill about 1 cup, maybe more? And what do you think is the most that could be coming back in samples? I heard 67,000 miles, I think, at the time of release of the sample container. Is that the closest that OSIRIS-REx will actually come to Earth, or does it get any closer than that? And lastly, when will this science campaign begin? Might it begin by the end of the year? Thanks.
Sure. I think I'll take the first and the last question and turn it over to Sandy or Rich for the spacecraft attitude question. So the 250 grams is a little over 8 ounces, which is a cup. It really, of course, the volume depends on the density, but we think Bennu is really low density material. Just for reference, a rock that you would find, say, out here in the Utah desert, about 3,000 kilograms per cubic meter. The bulk Bennu asteroid is about 1/3 of that, which is just above that of liquid water, which is a shockingly low density for geologic material. And then when we looked at what happened when we made contact with the asteroid surface, it was about half that. The area where we contacted the Bennu was about 500, so 1/6 the density of your average rock. So a cup is a good visual assessment. Of course, we don't know how the material is going to respond in the gravity field of the Earth, and it may compact, but based on what we know about the bulk density of Bennu and the mass that we estimate that we've collected, that's roughly of order of 1 cup. In terms of when the science campaign is going to start, I'm obviously pushing for as fast as possible. And the good news is we've worked with our colleagues at Johnson Space Center to identify the ability to sample very quickly in the processing. When we stowed the TAGSAM device inside the return capsule, It was leaking material. It was a moment where we rallied, overcame the obstacles, and safely got the material stowed away inside the return capsule. It was leaking material around inside the science moment where we rallied, dust, overcame the obstacles, and safely got the material stowed away inside the probably as it was leaking material around inside. There's going to be a moment where we rallied and overcame the obstacles, and safely got the material stowed away inside the probably as it was leaking material around, which is going to be a moment where we rallied, dust, overcame the obstacles, and safely got the material stowed away inside the probably part is leaking material around, which is going to have a moment where we dust, overcame the obstacles, but there's already part is leaking material around, which is going to have a moment where
The remainder of Sandra's site and assembles into a spacecraft pushing the limits of its thermal design. Beginning in 2029, it will chase down and investigate Apophis, a 1,200-foot stony asteroid destined to make an exceptionally close flyby of Earth. After 13 years in deep space, at the start of a new decade, alone on a new world, the journey will continue.